This is a window air conditioner. And this is a dehumidifier. What's the difference? This one's got a bucket. Hello, you're about to learn a lot about dehumidifiers. You're probably looking at this video's length and thinking, how the heck is there that much to talk about dehumidifiers? Well, it's simple. I'm a nerd. But I'm making this video because these machines have a simple mission with perplexingly confusing side effects. Most everyone knows what they do. They remove water from the air and decrease humidity. But the ramifications of that are, I'd wager, not very well understood. I myself didn't realize something pretty profound about these until quite recently, so today I'd like to talk about how dehumidifiers work. They're actually doing something pretty amazing, and when you understand the details, it might cause you to reevaluate where and how best to use them. This video is kind of all over the place, so rather than bury the tack too deep, I'll get right to the brass leads. The purpose of these machines is not to make you comfortable or even to help your air conditioning system. They absolutely will not do that. This might rub against your intuition. We all know from experience that humid air sucks when it's hot outside, and make air less humid is like its job. But before you run out and grab one of these things thinking it'll help in the next heat wave, there's a giant catch you need to be aware of. The process of dehumidifying the air generates heat, and it's a lot more heat than you might expect. This little machine can put out as much heat as a space heater, and larger ones will easily exceed that. And you probably don't want to be running a space heater during a heat wave. Now, where that heat comes from is fascinating, and it creates some really interesting implications when you use a dehumidifier alongside an air conditioning system. Those implications are really the main point of this video, but to fully understand them, we have to get pretty deep into the weeds. Which we will, hence the runtime. But long story short, if you don't have a significant and chronic humidity problem somewhere in your home which requires attention, there's really no point to having a dehumidifier. It's just going to make a lot of heat, a lot of noise, and waste your money. So what qualifies as a humidity problem? Well, as a general rule, if indoor relative humidity persistently stays above about 65%, though you'll find disagreement on the exact number, that's bad. That can lead to mold and mildew growth, which is unpleasant and dangerous. In addition to that, high humidity can accelerate corrosion on things that corrode and quicken material degradation in materials that degrade, so it can ruin your belongings. And if that's not enough, high moisture environments are more likely to attract certain pests. And if the damp gets real bad, it can even cause structural issues. So, if you live where the air gets moist a lot, dehumidifiers are common. They're practically a staple of Midwestern basements and crawl spaces during the summer months, especially when people have problems with stormwater seepage down there. Did you catch, though, that I said basements and crawl spaces? There's something unique about those areas. They're not generally conditioned, or if they are, such as with a finished basement, they're often poorly conditioned compared to the rest of a home. The main issue down there is that, since those areas are partially underground, in the warm months of the year they're typically cooler than the outside air temperature. And that leads to persistently elevated humidity. Now, it's important to understand why that is the case. When we talk about how much water vapor is in the air, we usually discuss relative humidity. Fun fact, though, relative humidity doesn't actually tell us how much water vapor is in a given volume of air. But that's fine. We don't actually need to care about how many water molecules are in a cubic meter of air. Relative humidity tells us what's usually more important: air's current ability to absorb more moisture. It's expressed as a saturation percentage, meaning air with 50% relative humidity is 50% saturated, and thus it has absorbed half as much water vapor as it theoretically can. But there's a wrinkle to this. Air's total capacity to absorb moisture depends on its temperature. Air can absorb more moisture the warmer it is. So, if you take a known volume of air with a known saturation percentage and heat it, its relative humidity will actually fall. It has exactly as much water vapor in there as it did before we warmed it up, but the air's increase in temperature unlocked more capacity for it to absorb water vapor, which ultimately lowered its relative humidity. This is why the indoor air is usually very, very dry in the winter months. Elevating the indoor air temperature causes relative humidity to fall. But of course, the opposite is also true. If you take air and cool it down, it loses its ability to hold on to moisture. And that means the same volume of air, when chilled, even though we haven't added any water vapor, becomes more saturated, and thus its relative humidity goes up. What this means for a house or structure is that when there's any air exchange at all between the cool basement or crawl space and the outside air, or even just the rest of the house, relative humidity will be persistently higher in those cooler spaces. That means it's harder for liquid water to evaporate down there, which in turn means wet stuff dries out more slowly. And that's the problem. If humidity levels are elevated enough, stuff will dry out so slowly that you risk damage to whatever's down there, or even your home itself. So what do you do in that situation? You condition the air. Dehumidifiers technically are a form of air conditioning, but they don't provide cooling. They simply extract moisture from the air and collect it in a bucket, or send it down a hose to a drain. That makes them less energy intensive than cooling, and for a space that's already kind of cool but a little too damp, they make perfect sense. Simply pick a humidity percentage you'd like it to maintain, and it will switch on when the air's too humid, begin extracting water from the air, and then switch back off once humidity is back in range. Now, I don't have a basement or crawl space at home, but I do have a garage, and that space is not conditioned at all, which isn't necessarily a problem and genuinely isn't in the winter months. But I live in the Midwest, and in the summer months, it can get quite humid outside. I store a good deal of stuff in my garage which I don't want to be damaged from that humidity. And that's why I have this little dehumidifier. It keeps the air in the garage from exceeding 50% humidity, and thus keeps all the stuff out there nice and dry. Even when I come home in the rain and park a very wet car in the same space with all that stuff. As the car drips water onto the floor and starts to dry out, the air in the garage starts to get very wet. But the dehumidifier always notices it's getting a little bit damp in here and switches on. And that is the point of a dehumidifier. It keeps the air dry to protect your stuff. That's what it's for. Though it does have the side benefit of helping the car dry off a lot faster. That's pretty neat. Before we explore how they work, I want to give two pieces of advice. First, if you are in actual need of a dehumidifier, for it to be any good at all, it needs to cost more than $100, and it needs to be a fairly heavy and cumbersome machine. This little one, which is the smallest capacity you can get from a mainstream brand, came with casters because it weighs about 30 pounds. I'll show you what's making it so heavy shortly, but please know and share with your friends that cheap machines that you can easily pick up are useless junk. This thing from Amazon, as far as I'm concerned, is a piece of e-waste which should not exist. This has no business calling itself a dehumidifier, as it can't even counteract the added moisture from your average human breathing. There are a lot of purported dehumidifiers just like this for sale these days, which simply do not, in fact, do that. And they're starting to show up in mainstream hardware stores too. In the US, dehumidifiers are rated in pints of moisture removal per day. I know. And this unit, which I will remind you is the smallest capacity you can get from a mainstream brand, is rated at 22 pints per day. Yet, Home Depot will gladly sell you this 3.2 pint unit from Magic Chef for $63, and Menards will sell you this 1 pint machine for $70. So will Lowe's. Don't waste your time with anything like that and put it back on the shelf. And if you'd rather not waste your time emptying the bucket from a real dehumidifier, but you also don't have access to a drain where you need to put it, before you resign yourself to the bucket brigade, look into getting one of these. This is called a condensate pump. It's a tiny, self-contained sump pump which you can drain a dehumidifier into using an abridged garden hose. And once the dehumidifier fills this sump with extracted water, a float switch is tripped and the pump will turn on. Then it pumps that water somewhere else. You can easily hook vinyl tubing up to these things, and if you've got a reasonable way to run that tubing to another room with a sink or drain, or even through an outside wall, it will make your life a lot easier. Some dehumidifiers are now being sold with built-in pumps, but in my experience, they don't work that well. I bought one some years ago, and its pump broke after less than a year, so I ended up having to get one of these for it anyway. These dedicated pumps are much more robust, though they can still fail, so if you're using one where an overflowing pump would cause a mess, you should periodically check on it to confirm it's working. But with that out of the way, why is this such a heavy and cumbersome machine? We should probably take a look inside. And through the magic of having a broken one, I could tear this bigger fella apart with reckless abandon, and what we find inside is an air conditioner. These are all the same parts we find in a small window air conditioner like this. In the dehumidifier, they're simply rearranged. Here's the compressor, here's a blower fan to move air through the evaporator coil, here's the evaporator coil itself, and then, sitting right behind the evaporator, is the condenser coil. That's... If you know anything about air conditioners, this arrangement will seem more than a little strange. But it actually makes sense, given what the purpose of this device is. It's not an air conditioner. It's a dehumidifier. But wait, don't air conditioners also dehumidify? Why, yes, they do. And that's why this is weird and complicated. This dehumidifier literally is an air conditioner, but it's controlled by a humidistat rather than a thermostat, and it has provisions to collect the condensate that an air conditioner typically sends down a drain or simply lets drip outside. Other than the different controls and the float switch that will shut it down when the bucket is full, this is the same machine that cools air, except it doesn't cool the air. In fact, it makes the air very hot when it's running in a humid environment. I suppose I should demonstrate that. I know! I'll set up a wireless hose! I put this dehumidifier in an enclosed bathroom and then put one of my temperature data loggers on top of it in the airstream of its exhaust. Then I switched it on and let it run non-stop for an hour. When operating, this small unit only consumes about 300 watts of power, which is not very much. If we were releasing that into the room as heat, it would raise the air temperature a little bit, but not a whole lot. And that's what we see. Over an hour of adding 300 watts of heat to the room, the exhaust temperature slowly rose, and by the end it had reached about 90 degrees Fahrenheit, roughly 32 Celsius. But then I switched on the arch nemesis of a dehumidifier, a humidifier. And in fact, two of them. Working together in that little bathroom, they dramatically increased humidity levels. But the dehumidifier worked diligently to undo that, which you can see as this fairly steady drip of water coming out of the hose. But notice what happened to the dehumidifier's exhaust temperature once the battle began. It climbed significantly. In just 15 minutes, it was above 100 degrees Fahrenheit, and by the end of the hour, it was tickling 105, about 40 Celsius. That might not seem like a huge increase in temperature, but these machines move a ton of air through them. So it's actually quite a lot of heat energy being expelled. And that's despite only using about 300 watts the entire time. How and why is there so much extra heat all of a sudden? Well, it's because of two things: latent heat and latent heat. To help explain this, I want to set the dehumidifier aside for a moment and go over how an air conditioner works. And I promise, this isn't just another chance for me to explain the refrigeration cycle. It's actually very important to understanding the whole picture here. But if you're not a newcomer to this channel and already know the basics of heat pumps and what coefficient of performance means, then you can go ahead and skip to
2756
if you'd like. So, an air conditioner is a machine which is exploiting the physical properties of a chemical known as a refrigerant in order to move heat energy from one location to another. And when you do that, the location which is getting energy removed from it becomes cooler. We can do this because refrigerants have very useful relationships between their boiling points and their pressure. The refrigerant inside this air conditioner, difluoromethane or R32, is normally a gas, and at atmospheric pressure, its boiling point is about -35 degrees Fahrenheit. In other words, you'd need to get it that cold in order for the gas to transition to a liquid. But we've trapped some of this gas, in fact 7.58 ounces or 215 grams of it, inside a big loop of piping. And that allows us to do some very interesting things. When this machine is operating, a mechanical compressor, that's this fella here, squeezes our gaseous refrigerant and forces it into this maze of piping. This is what's called a heat exchanger. All of those fins attached to the copper pipe looping back and forth help to quickly transfer heat energy from those pipes to the air. And a fan helps speed up that process even further by moving lots and lots of air through these fins. We need to do this because once the refrigerant exits the compressor, it's under very high pressure, typically above 300 psi. All that pressure is squeezing the refrigerant molecules together, which has the effect of dramatically elevating the refrigerant's boiling point temperature. In fact, under these sorts of pressures, the refrigerant's boiling point becomes higher than outdoor air temperature, typically by about 20 degrees Fahrenheit. This ultimately means that after it leaves the compressor, the refrigerant cannot remain a gas. The pressure in these pipes is too high and the ambient air temperature is too cold. So, the refrigerant inside begins condensing into a liquid. That's why we call this heat exchanger the condenser. And as the refrigerant condenses, it releases lots and lots of heat. Why? Hold that thought. Once sufficiently cooled down by all the air being forced through the condenser, liquid refrigerant begins to stack up at the end of the condenser's piping, thanks to a restriction known as a metering device. That's there to limit flow and maintain a pressure imbalance between the two sides of the refrigeration circuit. After the liquid refrigerant passes through the metering device, it moves into a second heat exchanger. And thanks to the suction created by the intake of the compressor, inside here the pressure is relatively low, perhaps 120 psi. That causes the refrigerant's boiling point to plummet, landing somewhere around 40 degrees Fahrenheit, about 5 Celsius. That's much colder than room temperatures. So, once the refrigerant makes its way into here, the air in a room is actually hot enough to cause it to boil off and become a vapor again. Since the refrigerant vaporizes in this heat exchanger, we call it the evaporator. And when the liquid refrigerant starts boiling inside of these pipes, it gets very, very cold. Why is that? Well, key to understanding the refrigeration cycle is that the refrigerant cannot boil away until it absorbs its latent heat of vaporization. That's the heat energy a substance must absorb to change phases from a liquid to a gas. Now, latent heat is very strange. Unlike sensible heat, which we experience as temperature, we can't feel latent heat or even detect it with a thermometer. For instance, when boiling water on a stove, if you're measuring the temperature of the liquid water with a thermometer, you will see it slowly and continuously rise as the water absorbs heat, and that's what you would expect. But then, it will get stuck at its boiling point temperature. Which is kind of weird, right? I mean, boiling water is very hot to us fragile humans, but compared to the temperature of a flame or a glowing heating element, it's quite cold, and so it's still going to absorb lots of heat energy from a stove. Yet, despite the fact that it's absorbing lots of heat, it's not getting any hotter. The temperature is just stuck. Now the reason is that once it's at its boiling point, the only heat energy the water can absorb is latent heat. And rather than increase the temperature of the liquid water, that heat energy is transforming the liquid water into its gaseous form, water vapor. We can observe this as violent bubbling at the bottom of the pot, but the thermometer doesn't show us this. All it sees is the fact that the water is at its boiling point temperature. Now, very importantly, all the latent heat energy which turned the water into a vapor is now stored in that water vapor. It didn't disappear. That heat energy is what's keeping the water at a higher state of matter. So let's bring this back to the air conditioner. When the liquid refrigerant enters the evaporator, the pressure inside is so low that its boiling point falls below ambient air temperature, meaning the refrigerant cannot remain a liquid. But to actually vaporize, it has to absorb latent heat energy. It first gets this energy from itself. This is why it immediately becomes so cold. It will use its excess heat energy to begin boiling, which causes its sensible temperature to fall until it's at its new boiling point temperature, and, like the water on a stove, it gets stuck there. But the refrigerant needs much, much more heat energy to completely vaporize. That's why the evaporator is also a heat exchanger. We need all these fins to help transfer heat energy from the air in the room into the cold refrigerant boiling inside the pipes. And when heat is transferred from the air into a colder substance, the air itself gets colder. Once the refrigerant has completely boiled away, the now gaseous refrigerant contains lots more energy than it did moments ago. It's still holding on to its latent heat energy that it just took from the room's air to become a gas. And here's the amazing thing. Simply by taking another spin through the compressor, we can force the refrigerant to get rid of that heat energy. Once repressurized by the compressor and sent back to the condenser, the refrigerant's under high pressure again, and its boiling point is back up in the well above ambient air temperature range. Since it's once again not possible for it to remain a gas, it will spontaneously condense. And as it does that, it releases the latent heat energy it just absorbed. Which means it gets hot. At a pressure of 350 psi, the refrigerant's condensing temperature will be about 105 degrees Fahrenheit, or 40 Celsius. So it's gonna be that hot once it starts to condense. And to allow it to keep condensing, we need to help it get that heat out as quickly as possible, hence all the fins and the fan. And of course, once it's condensed, it ends up back at the evaporator and the whole process repeats. The refrigerant is simply traveling in a loop, and the process runs continuously so long as the compressor is operating. Now, I want you to notice two things. One, the condenser has the same basic structure as the evaporator. This is because it will be releasing just as much heat from the condensing refrigerant as the evaporator absorbs when the refrigerant boils. And two, notice that the condenser is in a very different location from the evaporator. This is the basic principle behind a heat pump. Air conditioners are heat pumps, and they use the refrigerant as a working fluid to capture heat energy from indoors and move it outside, which results in the indoor air getting colder. When installed in a window, this machine's heat-absorbing evaporator coil ends up inside the home, and the heat-rejecting condenser coil ends up outside. So it pumps heat from inside to outside, which cools the indoor air. This is also how your refrigerator works, by the way, though it's just got to get heat from inside the box to outside the box. And the hot new thing is for heat pumps to be reversible. That way they can also absorb energy from outside air and bring it inside to produce heating. It's actually not new at all, but we've gotten much better at making them work in cold climates. But anyway, there's one last thing to know about heat pumps. The actual work this device is doing is mechanical in nature. It's using an electric motor inside this enclosure to spin a mechanical compressor which compresses a gas. And that's all it's doing. The whole refrigerant turns into a liquid and back part happens naturally as a result of heat transfer. It's absorbing and releasing its latent heat energy all on its own. The machine is simply creating the conditions for that to happen, and it uses heat exchangers and fans to speed it up. Because the refrigerant condenses and vaporizes separately to the act of compressing it, the refrigeration circuit is actually capable of moving more heat energy than is required to run the compressor. We call this the coefficient of performance, and when you get, say, 3 times as much heat moving capacity as you do input power, that's a COP of 3. Now, in an air conditioner like this, that would mean that for every watt of input power, you get 3 watts of cooling power. That's precisely how this little window unit, which is rated for 5,000 BTUs per hour, equivalent to roughly 1.5 kilowatts, only draws about 500 watts from the wall. The motors in the compressor and fan assembly consume that much power, but the refrigeration circuit is producing 3 times as much cooling power. And that is precisely why the dehumidifier has all the same parts as this air conditioner. You're getting extra heat moving capacity because the refrigeration cycle is awesome. Except, well, wait a minute. Yes, this machine has all the parts of a heat pump, but it isn't pumping heat anywhere at all. The condenser, which in an air conditioner has to go outside so it can actually get heat energy out of the building to cool it down, is, here. It's sitting literally right behind the evaporator and in the same airstream. Which means that immediately after air is drawn through the evaporator and chilled by the refrigerant absorbing latent heat energy, the air gets heated right back up on its way out by the refrigerant releasing latent heat energy. What's the deal? Well, we don't actually care at all about moving heat in this case. We just want to make a cold surface for water in the air to condense on. That's one way we can get water vapor out of the air, and the reason that works goes back to relative humidity. Remember that air can only hold on to so much water vapor, and the cooler the air is, the less water vapor it can absorb. This means that if you're able to cool it below the temperature at which air would become fully saturated and at 100% humidity, which by the way is a temperature we call the dew point, well then suddenly the air is going to have too much water in it, and the excess moisture will precipitate out of the air and onto cold surfaces. That temperature is called the dew point because that's why dew happens. You could say it's the dew process. Hey, side note, That was an awful pun, but did you know that due process, D-U-E, due process, is really just a fancy way of saying everyone is innocent until proven guilty? Last I checked, that's a core belief that all Americans share. If for some reason you no longer feel that everyone deserves the presumption of innocence until they are proven guilty, I think you might be having some un-American thoughts at the moment. Might want to get that checked out. Anyway, that's enough reinforcement of societal norms for today. You've experienced water condensing on cold things many times before. Cold drinks sweat in the summer months because the air right next to the cold surface of a can or glass becomes cooled below the dew point, so dew forms. That water used to be water vapor in the air, but the cold surface of the can caused it to condense. A dehumidifier is simply a machine with a very large cold surface that we force air through so that we can cause the same effect at a much larger scale, so large that we can decrease the humidity in an enclosed space, or even an entire house. Now, as we know, the dehumidifier doesn't cool the air in a room, but it is still using a refrigeration circuit to do its job. I don't know precisely what coefficient of performance this machine runs at, but for the sake of the video, I'm going to assume it operates with a COP of 4. That means, since this machine draws about 300 watts when it's running, it produces 1200 watts of cooling power in the evaporator right here. But of course, that also means it's producing 1200 watts of heating power in the condenser right in front of it. Those numbers are always going to match. Which would imply that since the condenser and evaporator are in the same airstream, their combined heating and cooling power will always cancel each other out. But that's not what happens! See, refrigerants aren't the only substances with a latent heat of vaporization. All substances have that, including water. Just as liquid water needs to absorb latent heat energy in order to vaporize, water vapor needs to release that latent heat energy to condense into a liquid. This always happens whenever water condenses, but it can be incredibly difficult for us to notice because it's latent heat and we can't feel it. For instance, when you grab a cold beverage from the fridge and condensation starts to form on its sides, that condensation doesn't feel hot, because it isn't. Those water droplets will have a sensible temperature pretty close to the dew point temperature. But the water will impart its latent heat into the can as it condenses, causing the contents inside to warm up much more quickly than if the air was perfectly dry. And that heating effect won't stop until the surface of the can is above the air's dew point temperature. Alright, and where does the dehumidifier fit into all this? Well, its whole job is to get water vapor out of the air, which it does by forcing it to condense onto the cold surface of the evaporator. And that means it's going to have to deal with the latent heat of water vapor. And how exactly does it deal with it? By converting it into sensible heat which we can feel. That's why the exhaust got so hot after I switched on the humidifiers. Now, I don't think the reason that happens is very easy to intuit, but it's pretty dang fascinating and is the key to this whole video, so I'm going to do my best to explain it. If the air in a room has no moisture in it at all, then when it goes through this dehumidifier, nothing would really happen. The air would be chilled by the 1200 watts of cold the evaporator is sucking out of it, but then it would be heated right back up by the 1200 watts of heat being released by the condenser. Since the two coils are right next to each other, the air coming out of the machine should be essentially the same temperature it was when it entered, plus 300 watts of heat from the motor windings. When humid air is drawn through the cold evaporator, though, weird stuff happens. Its cold surfaces will cause the air passing through it to fall below the dew point, and that forces water vapor in the air to begin condensing into water on the surfaces of the evaporator. And when that happens, as it always does, the water releases its latent heat energy, which the refrigerant absorbs. But it's latent heat. It's heat we cannot feel and thermometers cannot register, which causes a very strange effect. No matter what's going on, the evaporator can only absorb 1200 watts of heat total. So, if it's absorbing water's latent heat as it condenses, then it's actually losing the ability to cool the air that passes through. For example, if it's absorbing, say, 800 watts of latent heat from water condensing on it, then 2/3 of the evaporator's cooling capacity is going towards a process which does not lower the air temperature. However, there's a fact we cannot get around. The evaporator still absorbed 1200 watts of heat. We couldn't feel 800 watts of it because it was latent heat, but it was still heat that was absorbed by the refrigerant. With 1200 watts going into the evaporator, 1200 watts has to come out of the condenser. And it does. The condenser releases all the heat the evaporator absorbs. Latent or not, it doesn't care. And the total is always 1200 watts. But with the 800 watts of cooling not happening because of condensing water, we experience a surplus 800 watts of sensible heat coming out of the condenser. All of the latent heat the evaporator absorbed becomes sensible heat when the condenser rejects it. Add that to the 300 watts of heat coming from the motor windings, and now there's 1100 watts of sensible heat coming from this little machine. That's why the air leaving the dehumidifier is hot. This machine is converting the latent heat from condensing water vapor into sensible heat we can actually feel. And it just plops that heat right into the room. I find this incredibly fascinating because I'm a heat pump nerd, and this is one of the most visceral ways I've found to experience a machine generating much more heat than it apparently should. It seems impossible for a device which only draws 300 watts from the wall to produce air as hot as this does. But that's precisely what happens thanks to the power of a heat pump. But this isn't just trivia that's fun to play around with, it's actually a very important concept to understand because of how it relates to comfort and cooling. Most people agree that when the weather is warm, drier air is more comfortable. But while these machines can and will certainly dry out the air, the basic reality here is they're going to release a lot of heat to do that. Less when the air is already fairly dry, but even at 50% relative humidity, these things can produce a surprising amount of heat. Since they're usually controlled by a humidistat, it won't produce that heat constantly, just when it needs to run to lower humidity. But it might as well be a space heater when it's running. So don't expect them to make you comfortable, because they don't. That's not their job. They make otherwise humid environments safe for things which can be affected by moisture damage, and that's the extent of their role. If you're wondering how I can say that with such confidence, well, now it's time to imagine what would happen if you use a dehumidifier when you also have air conditioning. An air conditioner also has a cold evaporator absorbing energy from the air, so it also has to deal with the latent heat load from water vapor in the air condensing on it. But unlike the dehumidifier, an air conditioner can move that heat outside as it deals with it, which means, for our intents and purposes, it's gone. But the air conditioner still faces the same problem in that it can only move so much heat. And for every watt of its cooling capacity it spends condensing water out of the air, a watt of sensible cooling power is lost. This means when the air is extremely humid, an air conditioner is mainly just producing a lot of water and seems to struggle to cool the air temperature. When that's happening, you might think, well then add a dehumidifier. Give it the job of dealing with that water vapor so the air conditioner doesn't have to. But have you spotted the problem? While the dehumidifier will absolutely reduce the latent heat load that the air conditioner must deal with, It won't actually reduce the total heat load. It simply turns the water's latent heat into sensible heat, which the air conditioner will still have to deal with. What I'm saying here is that using a dehumidifier in a space that's already air-conditioned generally doesn't help. If you are cooling the air anyway, the air conditioner will generally remove enough moisture to keep everything safely dry. There are situations where adding a dehumidifier to your HVAC strategy can make sense. For instance, in the shoulder seasons, it might be getting too damp inside when it's not warm enough to run the air conditioner. And sometimes it can be legitimately necessary. If your air conditioner wasn't sized correctly, it might not be handling the moisture on its own. This whole can of worms, the latent heat load of water vapor, is precisely why sizing an air conditioner correctly is so important. It needs to run fairly long cycles for it to actually extract water from the air, and an oversized air conditioner can produce too much sensible cooling too quickly, which causes it to run short cycles which don't effectively dehumidify. Although modern variable capacity systems are much more flexible and they are improving the situation greatly. Still, even with an optimal air conditioner, if you have bad enough moisture ingress issues from poor air sealing or seepage, a dehumidifier can still be necessary. But in an ideal world, assuming you have air conditioning and you regularly use it, you shouldn't really need a dehumidifier at all, except in unconditioned or poorly conditioned spaces like basements, crawl spaces, garages, etc. But there is one last wrinkle. An air conditioner can only get the air so dry. Because air's dew point temperature falls as humidity does, before long an air conditioner reaches humidity equilibrium. At 72 degrees Fahrenheit and 50% relative humidity, the dew point is about 52 degrees Fahrenheit. And the evaporator coil in a properly functioning air conditioning system doesn't get much colder than that. So at ordinary room temperatures, an ordinary air conditioner can't drop humidity much below 50%. If you truly need or want it lower than that, a dehumidifier can get you a little bit lower, and most allow you to run them non-stop if you wish. Just keep in mind it'll be working hard to do that, consuming energy of its own, and it will produce more heat for your air conditioner to deal with. But can they save money? Well, that's a big fat "it depends." I mean, it's a concrete yes if you have damp problems and a dehumidifier saves your stuff from damage. But when it comes to energy costs, that's not easy to determine. Assuming a dehumidifier can remove more moisture per kilowatt hour than your air conditioner can, then so long as your air conditioner can keep up with the extra heat it's producing, that might lower your energy costs a bit. But to be honest, I wouldn't expect it to. These things are great at what they do, but they aren't exactly energy misers, and full-blown air conditioning systems, at least recent ones, are really energy efficient. High-end systems with variable speed blowers and compressors can even alter the ratio between latent and sensible heat loading by tinkering with airflow and refrigerant pressures. Slowing air down can get the evaporator colder, which will remove more moisture, and with the right sensors you can make sure the coil doesn't ice up. But even with basic air conditioning, if it's keeping your home dry on its own, there's really not much a dehumidifier is going to do for you. It's just going to make noise for no good reason. The only situation where I personally think of a dehumidifier as a potential cost-saving thing is when you're away from home and not using air conditioning at all, but you still want to ensure indoor humidity doesn't get too high. If you don't care about the temperature, well then you should be happy to let a dehumidifier run its little heart away. That's definitely going to be more cost-effective than cooling the place when nobody's home, and a warmer indoor temperature compared to outside air tends to reduce humidity issues anyway. But unless you travel a lot, or like you've got a vacation home somewhere, I would be very surprised if you'd actually get your money's worth out of the purchase of a dehumidifier. Also, to make a single dehumidifier effective for an entire house, you'd probably need to use your HVAC system's fan setting to move air around, and you'd be surprised how much power those blower motors use. It's usually a couple hundred watts at least. Alright, so now it's time to close this video out, which I'll do by acknowledging the flaw of dehumidifiers like this. These don't work very well in colder temperatures. And the temperature doesn't even need to be that cold for them to stop working so well, or indeed at all. These things are built to a cost and use very simple refrigeration circuits. They're either running or they're not. And this means that the operating pressures in the evaporator and condenser are going to depend mostly on the ambient air temperature. And when the air temperature gets somewhere around 55 degrees Fahrenheit or colder, that's about 13 Celsius, the refrigerant pressure in the evaporator might be low enough for the refrigerant's boiling point to be below the freezing point of water. And when that happens, the evaporator will freeze the water that condenses on it. And that will eventually plug up the evaporator with ice, and then air can't travel through it anymore. Now, any decent dehumidifier is going to be able to detect that this is happening and will shut off the compressor for a long enough period of time for the ice to melt. And that will happen pretty quickly since it keeps the blower fan running. But those periodic defrosts limit how much it can actually run and thus limit its effectiveness. However, this downside may not matter at all depending on your local climate. Where I live, you don't have to use a dehumidifier when the weather's cold. These things usually only get fired up in April or May, and then get turned off around October. Cold but damp just isn't much of a thing here. We only encounter that in the shoulder seasons, and never for long enough to require intervention. And remember, simply heating the air lowers humidity, and you don't have to heat it very much to have a dramatic effect. When it's 55 degrees outside, 13 Celsius, even if it's raining and the outdoor air is fully saturated with water, maintaining an indoor temperature of 68 degrees, 20 Celsius, will lead to indoor humidity of 63%. That's probably a little higher than ideal, but it's nowhere near as humid as raining. That's why humidity usually isn't a problem in the heating season. And here where it gets real cold in the winter, indoor air is so dry that we often want to add moisture, hence the humidifiers. The best part of Midwestern weather is that humidity is always wrong. Anyway, because the icing doesn't really happen when virtually anyone in the US actually needs a dehumidifier, this is the only kind that's sold here. The refrigeration cycle is just too efficient, and our weather patterns mean the icing issue is only a problem for a week or two, if that. But, as the old saying goes, there's more than one way to dry a flat. In a future video, we'll take a look at this, a rotary desiccant dehumidifier. This is a fascinating little machine which doesn't have the cold ambient performance problems a vapor compression dehumidifier does. But it does have several drawbacks, which is probably why I had to wade through tons of Amazon sludge just to find this one model for sale. That's for later though, and speaking of Amazon sludge, remember this thing? Well, this piece of garbage does technically remove moisture from the air, and it uses the same create a cold surface and blow air past it principle that the real boy dehumidifier does. But it's missing a refrigeration circuit and uses a Peltier element instead. Yeah, remember those? Those things that get put into novelty beverage coolers that don't work? Well, they also get put into dehumidifiers, which don't work. In that same bathroom with ambient humidity over 80%, this so-called dehumidifier produced this much water in 2 hours. That's 22 grams. Maybe this would be useful for like a terrarium or perhaps a small closet, but otherwise these things are just silly. There is a reason the catch buckets of a proper dehumidifier are so big. In the same 2 hours, this guy removed 1.2 liters of water from the air, 55 times as much. And yet, it only consumed 10 times as much energy as this thing did. That's the power of a heat pump, effective and efficient. If you noticed in the temperature logger chart I showed earlier that my testing happened back in August of 2024, well, that's because this video had an entirely different scope and concept back then, which I abandoned, in no small part because I would have finished it right when people would be putting their dehumidifiers away for the winter. I wanted to pit these three dehumidifiers against each other and was mostly interested in water extracted per kilowatt hour. But ultimately that was fluff against the bigger message of latent heat is very confusing and dehumidifiers do not help you stay comfortable. But when we look at the rotary desiccant machine, we'll definitely bring that topic back up. Because, well, it's not very efficient. But it is very interesting. So stay tuned. Anyway, that's enough reinforcement of societal... Wow, that's a mouthful. Anyway, that's enough reinforcement of societal norms for today. When we look at the rotary desiccant machine, we'll definitely bring that topic back up. What happened there? So it can ruin your belongings. And if that's not enough, yeah, I'm going to restart that. Relative humidity is 50% saturated and thus has absorbed... Blurb. It has yeah. Okay, so we got to read this one faster. So I screwed up for several reasons. Worked diligently to undo that, which you can see as this fairly steady dip of water. Oh boy.